Alright, let's solve this problem. We did a similar one in class today. But first, let's recall the definition of the area under the graph of a function above the x-axis between 2 points. And we know the area is a limit of the sum of many rectangles. So let's try to sketch a diagram first. Okay, this is what we have. And we approximately this is 1, and this is over here is 6. We don't have to use exactly the same scale, otherwise we won't be able to do it. So we can say this is over here, and when x is 6, this is pretty large number, but let's say we have something like this. All right. Okay, so the idea is that the area is the limit of the sum of these rectangles. We need to be careful. Usually we use the right end point to approximate these rectangles. So this is what we have. Okay. Let's first write down. So the area is the limit over here, and n going to infinity. N over here is the number of these rectangles. And we write down a1 plus a2 and keep going, an. A1 is the area of this rectangle, A2 is the area of this rectangle, and so on. Okay. Now, n over here is the number of intervals, number of subintervals, we sometimes say, subintervals. Okay. Now, if we look at the total length of this base over here from 1 to 6, we know this number b minus a over n is the size, is the length of the base. This is the base of each subinterval. Over here. So we know how to calculate the area. We just need to use this base over here and multiply it by this height. And we are saying we're going to use the right end point to calculate this height over here. And we know the function over here is x cubed plus 1. So we just need to find out what is the coordinate of this point. Now, because this is 1, we can actually draw the line over here so we can see things a little bit more clearly. So this is 1, and over here is 6. Okay. And each interval over here, this length from here to here is b minus a over n, because we have n subintervals. And this is going to be, in our case, 6 minus 1 over n, and that's 5 over n. And we look at the coordinate of this point, because this length is 5 over n, so this one must be 1 plus 5 over n. That's the first point we have over here, first right end point. So if we keep going, this second one over here is going to be 1 plus, now twice over here, because this is 1. One segment over here is 5 over n. The length of this one is again 5 over n. So we have twice of 5 over n. If we keep going, if we look at the ith one over here, this is the one we call it the ith one. Is I over here is any number between 1 and n over here. And this point over here, we can see the pattern. This is going to be I times 5 over n. And that's going to be the right end point of the ith subinterval. Now we can write down the formula for these areas. A1 is going to be simply base times height. Base is 5 over n. Times height, we have to use the function's value. So it should be f of, let's say we put x1 over here. And that's going to be 5 over n. And f over here. This point over here is, this is x1. First right end point is 1 plus 5 over n. Now remember, the function we are looking at is x cubed plus 1. So this is what we have, 5 over n. Just plug in this function. So x is this one, is 1 plus 5 over n, and cubed, and plus 1. So we can see this is the value of the function. That means this height over here. Now we look at the second one. So A2, second area. The base is the same because we have divided this interval into n subintervals of equal length. So we can skip this one over here, and we see this is going to be, the second point is 1 plus twice of 2 times this interval length, and we have cubed over here plus 1. Again, we see the function over here is x cubed plus 1, and this x over here is this value because it's the second right end point. So once we've done this, somehow we can see a pattern now, and then we will see the ith one, AI, is 5 over n, and we have 1 plus I times 5 over n, and cubed and plus 1, like that. And the last one over here, we see the last one over here, x is 6, but we can actually use the same pattern over here. So a, the last one, a sub n, is going to be equal to 5 over n, and then we have 1 plus n over here, 5 over n, right? And cubed and plus 1. We are almost done. Now we just need to put these expressions back over here. Then we have it. So a over here, the area is represented as a limit, and n is approaching infinity. That means we divide this area into many stripes over here. And the first one is 5 over n, and we have 1 plus 5 over n cubed plus 1. We are not worried about whether this sum can be found out. We just want to have an expression. 1 plus 2 times 5 over n, and cubed and plus 1. And we keep going just like this. And we write down the last one, 5 and and 1 plus n 5 over n, and cubed over here plus 1, right? Now, in our textbook, we also use the sigma notation. For the sigma notation, we just need this one over here. So this is going to be the limit. N is approaching infinity, and we use the sigma notation. This sum over here is the same as this one. I goes from 1 to n, right? And then we have 5 over n and 1 plus I over here, 5 over n cubed, right? And then plus 1. Okay. Sometimes this 5 over n can be pulled out of this summation. Now, you cannot put 5 over n in front of the limit because n is changing, but we definitely can do that. It's 5 over n and sigma I from 1 to n over here, and we have 1 plus I 5 over n cubed and plus 1. As we mentioned before, inside this limit, the expression over here, we can still see the function and also roughly the left end point of the interval, which is 1, and you can still see over here, and also 6. How can we see that? You can see that if I is n, that means at the right end point, the last one, then if I is n, then n they cancel. You have 5 plus 1 is 6. So we can still see that. Later on, we are going to define what a definite integral is in the same way. In fact, this is simply the definition from 1 to 6, this definite integral, and x cubed plus 1 and dx. This is simply the notation, again, for this limit over here. All right, thank you. Bye.